Should we start? Yeah, let's. I mean, maybe give this 2 minutes. 2 minutes for. So. Yes, it's Friday already.
And it looks like I can't share my screen.
Kacper, please.
There we go. I'll just wait for you. Go ahead and if we can.
Yes.
It's my last day today, so it's become kind of an evening routine to me. So I'm going to miss it, I guess.
I mean, so we can, like, we have free Sunday, right? So Sunday, yes. So no, Saturday, we limited our weekend to 1 day only. So yeah. On Saturday we have lecture. Okay, so I think that we can start the third lecture by Roman Krems. So yes, so I think the stage and internet connection is yours.
Thank you, Mikhail. Thank you, everyone. Good morning. I'd like to reiterate that if you have any questions, please don't hesitate to email me. I've received a few emails. I received a few emails yesterday, and yeah, I'll be happy to address those questions and answer them to the best of my ability by email. So don't hesitate to write to me. So what we're going to do today, we are going to talk about a couple more fundamental aspects of machine learning, one of which is model selection, which is going to be very important for us, in our discussion of how to select the best kernels for problems that we're going to address. And then we're going to look at some applications, applications from my group's research in particular. Okay, so before we begin, let me remind you some of the basic definitions, just to make sure that we're all on the same page. Of course, if you have a random variable, we have the mean of it defined like so, and the expected value. We're going to be talking about a lot of expected values today. Of course, is going to be defined like this. The variance is the expected value of x minus the mean of x squared, and the covariance for two different random variables is going to be defined like so. For a lot of the variables that we're going to be dealing with today, the mean of those is going to be 0. So this part and this part is going to be absent. So the covariance is just going to be the expected value of x times y. Okay, so that's just to make sure that we're on the same page. Okay, so we talked about Gaussian processes quite a bit already, and we're going to be using them for our applications today. So one bit that's remaining for us to discuss is how Gaussian processes are trained. Okay, so as in other kernel methods, one starts by choosing a function for the Gaussian process kernel. We're going to talk about what the kernel in the context of Gaussian processes means actually in just a couple of minutes. But yeah, one would start with by choosing a mathematical function for the kernel function. And then the parameters of this function have to be optimized somehow. So they're going to be optimized by maximizing this quantity here, the POY given x. Okay, so what is this quantity here? So if you recall our discussion of the Bayes theorem from yesterday, so you will recall that this quantity appears in the denominator of the Bayes theorem. Okay, and it's basically given by this integral here. You see what this quantity does? It takes the prior, okay, it multiplies it by the likelihood, by the model likelihood. So the model likelihood, as we discussed yesterday, depends on the data, okay? And then it integrates the product of these two over all of the random function values in this case. So when we integrate over a variable as theta in this integral, we say that we are marginalizing this variable. And that's why this term here, the term on the left-hand side, is going to be, well, as you can see, it's the model likelihood integrated over the function values here. And that's why it's called marginal likelihood. So this is marginal likelihood, okay? So we're going to be talking about marginal likelihoods quite a bit today. So it's important to understand this. Okay, so marginal likelihood for a Gaussian process can be expressed as in a closed form in terms of kernels. So let's see how this is done. So to answer this question, let's consider again the prior in our from this integral here. Okay, so let me remind you that theta, it represents collectively those beta coefficients from yesterday, the ones that we, in the coefficients of the neural network that we promoted to random variables. Okay, so so P of theta is going to be the unconditional distribution of the neural network outputs at the locations of the input space given by this data matrix here. So this is again our prior. Now, because the functions theta are drawn from a Gaussian process, so each value of theta is going to correspond to one of those random functions that I plotted yesterday in this distribution of functions that represents a Gaussian process, right? So because those functions are drawn from a Gaussian process, P of theta is basically a multivariate Gaussian. Okay, so what we're gonna now try to determine is what the covariance matrix of that multivariate Gaussian is. Okay, so again, when I say that P of theta is a multivariate Gaussian, this means that if I look at P of theta at xi and P of theta at xj, so these are those vertical cuts in the plots that I showed you yesterday. They're basically, they're both Gaussian with some covariance between these two distributions. So this and the covariance is going to be denoted by covariance of xi and xj. Okay, so what is this covariance? So we will choose the covariance of the Gaussian process prior to be the kernel function. So this is what the kernel function is in the context of the Gaussian process. And this is actually equivalent to the choice of the prior that we made in this mathematical derivation that we didn't actually go over, but in that derivation we chose the prior over the beta coefficients, those coefficients of the neural network. We chose them to be basically to be normally distributed with zero mean and some covariance matrix sigma p. Okay, and so now if you look at the covariance, this quantity here, so basically so you're going to have to look at the expected value. So the covariance is going to be the expected value of f of x and f of times f of x prime. Okay, so where f of x is your Gaussian process, that's your model. Okay, so now if you look at the expected value of f of x, so this part here doesn't have any random variables in it. So you can take it out of the expected value, and that's going to be just the expected value of beta. And because we chose the distribution of beta to have zero mean, this is going to be zero. Well, and that's actually why I'm writing the covariance as a simple product of f of x and f of x prime. Because in general, the covariance, as we said on the first slide today, is determined by f of x minus mean of f of x times f of x prime minus mean of f of x prime. But in this case, those means are going to be zero. Okay. Now, if you replace f of x and f of x prime with this part here, then you're going to get this. Okay. And then, of course, this is just the sigma p. Okay. And well, first of all, the sigma p, we have freedom in the choice of it, so we could choose it the identity matrix. So if this were the identity matrix, then you can easily see that this is our kernel function, right? Because this is our feature map from the input space to a high dimensional Hilbert space, feature space, right? So this is our feature map. Remember our discussion 2 days ago. So this times that, it's basically, it's a scalar product of two vectors that represent feature maps from the input space to the feature space, and we define, you know, those sort of scalar products to be kernel functions. Remember our discussion from 2 days ago? So that's what we did back then. So the only difference that we have between then and now is this metric sigma p here, because if it's not an identity matrix here, then you know, this is going to be somewhat different from the way we define kernel functions on day one. But because this is a covariance matrix, it's going to be so it can be written basically as a product of two other matrices, and we can absorb those two other matrices into the definition of the feature map. So that basically is equivalent to somewhat redefining what kernel functions are. And it doesn't matter, because at the end of the day, we're going to fit those functions. We're going to vary those functions in order to maximize marginal likelihood anyway. So, okay. So what we now see is that the kernel of the reproducing kernel Hilbert space that we talked about in our first meeting is nothing else than the covariance of the Gaussian process prior. Okay. Now our goal is to evaluate the marginal likelihood, which is this integral here. Okay, it's actually more convenient to work with the logarithm of that. So we're going to be dealing with the logarithm of that. Okay. Now, because this is a Gaussian with the covariance matrix given by the kernel matrix, and this is this likelihood is also Gaussian. So basically, we have two product of two Gaussians. So this integral can be dealt with analytically, and it can be written in terms of the kernel matrix. And the math is a bit tedious, but the final result is this. So basically, the log of the marginal likelihood for the Gaussian process can be written in this form, where you have the kernel matrix explicitly on the right-hand side. So then, so remember, the kernel matrix has the dimension of the number of training points by the number of training points, and each entry, each matrix element of the kernel matrix is basically just the value of the kernel function that connects the two training points. Okay. Now, so when you train a Gaussian process, basically you maximize this quantity by varying the parameters of the kernel function. So you basically, and to do that, you have to iteratively, I think there's a minus one here that's missing. So this should be inverted. So you have to iteratively invert this matrix, the kernel matrix, and you should, and calculate the determinant of the kernel matrix. So it's this inversion. Yeah, I apologize. So this should be to the power of -1. So this whole thing in the parentheses. So this inversion of the kernel matrix is actually what makes training Gaussian processes difficult when the number of training points is very large. So if you want to apply Gaussian processes to very high dimensional problems, you need to train those processes by a large number of training points. And of course, we know that numerically inverting a matrix scales as the third power of the dimension of the matrix. So this is what's going to limit the application of Gaussian processes to big data problems. But for small data problems, when the number of training points, this n here, is not very big, Gaussian processes are ideal. As we will see today, they're extremely efficient at inferring information. And moreover, you can, by suitably crafting kernels, you can actually design Gaussian processes that have extrapolation power. We're going to talk about that. Now, there's one more thing I want to, sorry.
I have a question to this. I heard of sparse Gaussian processes that scale instead of like n to the 3 with, I think, n to the k squared, where k is just some smaller number.
Sure.
Can comment on how this is reached?
Yeah. So basically, what you're doing, you're building an approximation to the full Gaussian process by sparsifying your data. So yeah, you could. There are different ways of dealing with this, and there are many ways of sparsifying, I guess, the data. yeah, so the whole idea is to get around this numerical difficulty associated with inverting the full kernel metrics. It's like, well, like I said, there's many approaches that people use, but one, for example, would rely on the fact that not all of the correlations in the entire training data are equally important, right? So you can, for example, break your kernel metrics into smaller matrices, perhaps. And I actually, have not done this myself, so I'm not entirely sure exactly how sparsification works. I mean, I may have done this on a couple of occasions, but without paying too much attention. But people do that. People do, but those would become approximate approaches. I mean, yeah. So if you want to include all of your training data fully into building a Gaussian process model, then you have to invert the full matrix that has the dimension of n times n.
Okay, thank you.
Yeah.
We have one more question.
Yeah,
Just
sure.
let me run.
So some years ago, Shalev-Schwarz proposed to use gradient descent-like algorithms to train kernel methods. And I would like to know if this is applied in Gaussian processes to train on big data.
Oh, I'm not sure about big data. I mean, like, the way you would the way you would maximize this marginal likelihood is by gradient based algorithms typically. So I don't know if that's what you're referring to. Probably not.
No. So if you do this, you're kind of optimizing analytically, but I'm just saying that he proposed to do the optimization in a gradient descent-like approach. So to update your parameters iteration by iteration. And I didn't see it applied much in literature. So I'm just wondering if you usually use it when you have like large amount of data and you have like a big matrix that you need to invert. Maybe it's more convenient to do first order optimization by gradient descent.
I see. So you're saying that instead of using this equation, just go for the marginal likelihood directly and try to optimize it. Well, what people often would do is use something like Markov chain Monte Carlo then. But for us, of course, this is the best approach because the kind of problems that we deal with, well, let me tell, I guess, the range of the applicability of this. I mean, what this is ideal for. So because we're limited by matrix inversion, we want to stay. So we're limited to problems that typically will have less than 100 dimensions, and which implies that you probably need on the order of 10,000 to 100,000 training points. And that's going to be pretty much your limit. And there's a lot of problems in physics that are a lot, lower dimensional than 100 dimensions. So this is where I guess this sort of formalism is the most useful for. Yeah, so there are papers out there where people try to extend Gaussian processes and kernel methods in general to big data problems. And I think the biggest kernel matrices that people have considered, I mean, like the last time I checked, this was something on the order of, 1 million by a million or 10 million by 10 million, something like that. So which basically is saying that, training a model by something like 10 million data points. Yeah, so the focus of much of our work is actually on applications in the opposite limit. So where I believe this is the most useful, and just finish my thought and I'll take a question. So where I believe this is the most useful is actually in the limit where you have very limited data and you want, like, say you have 100 of experiments and you want to maximize inference from those experiments. And so this is where Gaussian processes, I think, will do the best job, in my opinion, compared to pretty much anything else. And of course, the net limit is straightforward to train them. So was there a question?
Yes, thanks. And then another question.
We're good. Should I continue?
One more little question.
Yeah.
I mean, you're probably gonna talk about this, but I'm confused. What are the free parameters that you train in the kernel function? Is it like from the examples that you've shown, these hyperparameters, like the thing that's in the exponent, or is there something in the kernel function itself, like these lambdas that we're optimizing?
Yeah, it's well, I'll talk about this, but yeah, so it's like the exponents, like, well, pretty much anything, right? So anything that defines this function, right? So like in the simplest possible case, it could be a Gaussian function, and the variance of that Gaussian could be the parameter that you would optimize.
Okay.
But for our kind of problems, you know, we're going to be building much more complex kernels, and there's going to be many more parameters. And actually, for that reason, I should mention that, well, it's kind of obvious from this equation, but I should say this, that this marginal likelihood, it's marginalized over the random function values, over those data values, but it's not marginalized over the kernel parameters. So if you want to calculate the full marginal likelihood for a Gaussian process, you have to marginalize also over the Gaussian process parameters. And if your kernel is very complex, this is actually a very difficult problem. And this is going to be relevant for what we will be discussing later today. I just want you to take a mental note of that. So this marginal likelihood is not like it still corresponds to fixed parameters of the kernel function, and we maximize it by varying the kernel function parameters, you know, the hyperparameters. But we don't integrate over those parameters. So that's actually going to be important for later.
Mm-hmm. Thanks.
And I'll try to remember to mention this again when we see examples of kernel functions later on again. Okay. All right. So just to mention again that the key difference between Gaussian process regression and kernel ridge regression is again in the way they are trained. So in the way the parameters of the kernel functions are determined. You know, in kernel ridge regression, they're found by cross validation and the minimization of the validation error. And for the Gaussian process regression, they're found by maximizing marginal likelihood, just like we discussed just now. Okay, but this is just a side remark. So now this is a very important section. So model selection. Let's imagine, let's say we have built two models with two different kernels in the context of what we're talking about. So how to tell which one is better? So the Bayesian, is there a question? No. Okay, so the Bayesian approach gives us actually a formal way to deal with this question. Let's see how. So let's say we have a set of noisy data points and we have two different models, such as, for example, M1 and M2. So how can we tell which model is better? So we're going to be using the Bayesian view to answer this question. So what basically we will be calculating is the probability of a model being a good model given our data. So this is the probability that we can calculate using the Bayes theorem, right? So this probability is going to be given in terms of the probability the prior, basically that's the probability of a model. So if we don't have any information about the data, it's reasonable to assume that every model that we build is going to be equally good. So the prior, you know, we can set it to be the same for any model. Okay, and then of course, what we are after is really this, which is going to tell us, which is going to allow us to compare the probability that a given model is going to be better. So we can take this for two models, M1 and M2, and we can take the ratio of the two. And then if we do that, I mean, like the term in the denominator here is going to be the same, so it's going to cancel out. So then we have basically this factor times the ratio of the priors. So this factor here is called the Bayes factor. So this is basically and again, if you think about it, this is actually the marginal likelihood of the model. So this is the ratio of the marginal likelihoods. So the Bayes factor is going to be important. Okay. So yeah, this is just again repeating what I just said. So this part here is nothing else than the marginal likelihood, and this is now the full marginal likelihood, marginalized over everything. Like in the context of Gaussian process regression, this would be the likelihood marginalized both over theta and over the kernel parameters. So if we wanted to calculate something like this, we would have to integrate over the kernel hyperparameters. Okay, right. So right, so this is marginal. So now, like I said, if we don't know anything about the data, we could not do anything better than to say that the prior probability of each model is equal, and then the ratio of the posteriors. So this is the quantity that tells us which model is more or less likely to be better. Okay, so this ratio is going to be simply equal to the ratio of the marginal likelihoods. So we can use the relative magnitudes of the marginal likelihoods to tell which model is better. Now, theoretically, the trouble is, and in practice, it is very difficult to calculate marginal likelihoods. Like even for Gaussian processes, like I said, if we're going to build complex kernels with some, like say 20 parameters, we would have to do 20-dimensional integrals, and those integrals would have to be done numerically. Okay, so very quickly we run out of steam when it comes to calculating marginal likelihoods. Okay, so let's consider this problem from a different perspective. Okay, again, we have built two models with two different kernels. We want to tell which one is better. So when we train a model, we minimize a loss function, is in the kernel ridge regression, or maximize log likelihood. Okay, why not to just choose the model that gives a lower loss or bigger likelihood? Now, this we cannot do because of overfitting. And I was going to take maybe 5 or 7 minutes to actually talk a little bit about the generalization error and about the bias variance trade-off, because these are actually central concepts in machine learning. So let's do that. So the generalization error is really what we are after when we build models. So we want this error to be as small as possible. And this error is defined as, well, it's also called test error. And it's basically defined as the expected value of the loss function, given a fixed training set. So, and this is important, for a fixed training set, the expected value of that is going to be your generalization error. Now, this quantity is very difficult to calculate. The one for the fixed training set is very difficult to calculate. What is easier to calculate, and this is what people use to approximate the generalization error, is the expected prediction error. It's basically the expected value of this. So in other words, this is this quantity averaged over multiple training sets. Okay, so that's what we do. What we mean when we say this. Okay. So let's take a look. Let's take a look at this expected prediction error and analyze how it behaves as a function of the model complexity. Okay, because what's going to matter to us. So what we want to be able to do at the end of the day is compare models of different complexity. Okay. Yeah. Okay. So and this is where bias versus variance trade-off comes in. Okay, so again, we have our data that we're going to model by some function plus noise. So the function is generally unknown, and our goal is to infer it. So we build a regression fit, and so that's our. This is going to be our model. Okay, so now we want to test the performance of the model, and we calculate the expected prediction error at some point of the input space, which we call now x naught. So that's going to be our expected prediction error. So we're going to be averaging over all of the random variables in the square brackets. And what are the random variables here? Well, the first random variable, of course, is noise, right? So noise is random. So this is, we're going to be averaging over this. Now, the second random variable is actually the model. So why do I say that it is random? Well, it's because each time you change your training set, you are changing your model. So when you're averaging over training sets, different training sets, you're effectively averaging over models. Okay, So what we're going to do now, we're going to just expand this square here, expand the square here, and see where it leads us to. Yeah, so we're going to have, if we just expand the square, we're going to have this term here, and then we're going to have this term here, and then we're going to have this term here. This is trivial math. Now, this part here is just the variance of the noise. So there's nothing we can do about this. This is just given to us by the noise of the data. So what do you think is this term going to be? Perhaps you could tell me. So to answer this question, we're going to use one of these properties, like the expected value of the product of two random variables is going to be the product of the expected values. So we can write this as the expected value of noise times the expected value of this thing, but the expected value of noise is 0 because we're going to assume that noise is well, I guess it is centered on the function, the true function. Okay, so this term is going to be 0, and then we're just going to have to deal with this term. So we're going to, again, so how are we going to deal with this term? And this is just basically repeating what I just said. Okay, yeah, so we're going to deal with this term. Okay, so we're just going to expand the square and write it as this term minus 2 of this term. So you see, I took f of x naught outside of the expected value because this is not a random variable. This is just a well-defined function. It's a function that we don't know, but it's a well-defined function. Okay, and then we're going to have yeah, and then the square of the function is also going to be there. Okay, so what we're going to do now, we're going to add and subtract this product here, and then if we do that, then we have this general equation here, and if we look at this equation carefully, we'll see that this term here is basically the bias, well, the square of the bias of the model. You see, you have the expected value of the model minus the model minus the true function, right? So that's going to be the bias squared, right? And this whole thing is going to be the variance of the model. Okay, so this is the variance of the model. So basically what we're saying is that the expected prediction error is going to be decomposed into 3 terms. There's going to be a variance of data noise, which is given to us by the data. There's nothing we can do about it. But then there's going to be 2 other terms. One is the square of the bias of the model, and the other one is the variance of the model. Okay, and this is what, you know, and you see these two terms, you know, there's going to be a trade-off between these 2 terms, because as the model complexity increases, the variance of the model increases, but the bias of the model decreases. And this is depicted by this plot here that I took from this book called The Elements of Statistical Learning. Okay, so as you can see, if you look at the prediction error as a function of model complexity, obviously, if you look at it on the training sample, it's just going to go down, and this is going to be because as you increase the model complexity, you're going to be increasing model variance, and it's going to just be fitting the noise, and yeah, so you're going to be overfitting. But if you look at the prediction error on the test sample, it's going to go through this minimum here, and this minimum is determined by the trade-off between these 2 quantities. Okay, as you go left to right here, the variance increases and the bias decreases. Okay, so why am I saying this? I'm saying this because if we want to compare 2 models, okay, it's not sufficient to just look at something like log likelihood, okay, or something like the loss function, right? Because those quantities, they don't take into account the complexity of the model. We somehow need to be able to compare models of different complexity. So we need a good way to discriminate between models that also accounts for their complexity. Okay, so how do we account for model complexity? And there's several criteria that can be developed, but the best, in my opinion, one of them is the so-called Bayesian information criterion, which is defined as -2 of the log likelihood, well, the maximum value of the log likelihood, not the marginal likelihood, but the actual log likelihood. And then there's an additional term in this equation here, which where D is the number of model parameters and N is the number of training points. So you can see that this term here, so now you could use this as the metric to discriminate between the models, to compare the models. So this term here is going to penalize models with more parameters or more complex models. Okay, so yeah, so the lower the BIC as defined like so, I guess the better the model is going to be. And now, why do we know this? Why is this a good metric? Okay, well, it turns out that BIC as defined like so is very closely related to the logarithm of the marginal likelihood in the large in the limit of a lot of training points. So in particular, you have this approximate relation here, which can be obtained by applying the so-called Laplace approximation to the integral, which defines the marginal likelihood. So you see, this is the marginal likelihood. And we said earlier that within the Bayesian approach, this can be used to discriminate between the models. Okay, so like I said, if n is large, if this n is large, this integral can be approximated or can be shown to be very close to the value of the log likelihood. You see, this is not marginal likelihood, but the actual likelihood that corresponds to the model parameters with a hat here. So these model parameters maximize the likelihood. And then there's this additional term here. So this equation shows two things, right? So, well, one is that the marginal likelihood actually accounts for the model complexity. So that's why it is a good metric to actually compare different models. And number two, you can see that this quantity is actually is analogous to BIC, because if I were to take this equation and multiply it by -2 on both sides, then I would have -2 log likelihood here, and then plus d log n. So basically, -2 of that is equal to BIC, and yeah. So basically, if you're going to be, so you can use this to discriminate between the models, you can use this as well. Okay. So, and because of this connection to marginal likelihood, BIC can be used to estimate the posterior probability of each model by these simple equations. So where this is just a normalization factor here. So BIC, unlike the other model selection metrics, which we don't have time to talk about, BIC is actually asymptotically consistent as a model selection metric, which is basically to say that given the family of models, so if you have a family of models that includes the true model, the probability that BIC will select the true model approaches 1 as the number of training points goes to infinity. Okay. All right. So now this is this equation that I showed you just a couple of seconds ago again. And inspired by this equation, we can now adapt it to our Gaussian process problems. We can define a quantity, which we're going to call BIC by analogy, as the log of the marginal likelihood that we use to train our Gaussian processes. Remember, this is not the full marginal likelihood, but the marginal likelihood that corresponds to fixed kernel parameters. And so this is what we optimize when we train Gaussian processes. And then if we add simply this quantity here, where D is the number of free parameters, the number of hyperparameters, the number of parameters in the kernel function, okay? Then we have a metric that is equivalent to basically the full marginal likelihood for a Gaussian process. And we can try and use it to discriminate between models with different kernels. Okay, now, as we saw on the previous slide, or as I told you, this equation here is an approximation which is valid in the large n limit. Okay, in principle, this can be used to build better kernels, but in the large n limit. Now, the beauty of this is that we will see that empirically, we will see that it also works very well for low values of n, for very restricted data sets. Okay, so this is what we find in many of our studies, and we're going to see that. Okay, now this is what I've been telling you all along about. So how do we build the most optimal kernels? Okay, so we're going to start with conventional kernels. For example, the linear kernel, the RBF kernel, the Mattern kernel, the racial quadratic kernel. So if you build a Gaussian process model with one of those kernels, what you're optimizing are those parameters, like this R here, or this alpha and L. So this is what you're optimizing when you're maximizing the marginal likelihood. You could also simultaneously optimize the variance of the noise, which we don't always do, but one can do that as well. Okay, but in any case, so normally people would just choose one of those and build a Gaussian process and be happy with it. And of course, you need to make it accurate. And one way to make a Gaussian process accurate is by including more training points. Because this is a Bayesian approach, the more training data you include, the better your Gaussian processes will become. That's guaranteed. Okay. So we are interested in a different problem. We're interested in a problem where you have a restricted number of training points, and we want to make Gaussian processes better for a given set of training points, like say 100 training points. Okay, so for that we need to make kernels better. So, and this is the algorithm. So we're going to start with an ensemble of traditional kernels like this one, and then we're going to combine them to form products and linear combinations. So I'm going to basically use this sort of a search tree algorithm, which again starts with each one of those 4 kernels. I'm going to label them as RBF, Mattern, rational quadratic, linear kernel. So I'm going to build 4 Gaussian process models with these kernels, and I'm going to select the one of them that has the highest value of BIC as defined by this equation here. Okay, I'm going to select the one with the highest value of BIC, which is the one that's highlighted here, for example, as my base kernel. And then what I'm going to do, I'm going to take this kernel, I'm going to multiply it by all of these other kernels, and I'm going to form linear combinations of this one with all of these other kernels. And by doing this, I'm going to get 8 new kernels, right? Or whatever, like 6 or 8. And then I'm going to train 8 new models, and I'm going to calculate the BIC for each one of them. And then I'm going to select the kernel with the highest value of the BIC as my new base kernel. And then I'm going to take this process and iterate it. And so I'm going to go down and down this search tree, the search tree. And as I go, down the search tree, as the number of layers in the search tree increases, the complexity of my kernel will increase. Like, for example, in this particular case, my kernel represents a product of a rational quadratic and linear kernel plus the RBF kernel. Okay, and of course, as I go further down, the complexity increases, so I have more and more kernel parameters to optimize. It gets harder, but it also makes my kernels a lot better. Okay, so the algorithm is due to these people here. So they used it for structure discovery, basically for pattern recognition and things like that. And we've adapted it to physics problems. Let me illustrate to you how this works, and then we're gonna. Is there a question?
Yeah. When you go down this tree, are you not?
Sorry. You're muted. I can't hear you. Is this my problem or? Hello?
Yes, it was mic problem. You are back.
Okay, good. Yeah.
So the question is, when you go down this tree, are you not, like, if you test a lot of a lot of different models with the same data, are you not overfitting in the end? Like, because I mean, this big would just work if you basically don't select a prior model based on the prior big, right? like what I mean, for example, if you have, if you train like 100 neural networks and then you get the one with the smallest loss, even though they all have the same amount of parameters, you are basically overfitting because you basically go overfitting by selecting the best model.
That's right. You
don't have this problem here.
Yeah, you will have this problem here. As you go down this tree, at some point you will start overfitting. So if you look at the validation error, for example, it will go down and then it will start going up. So what we normally would do, we would stop increasing the complexity of the kernels, once the error turns around.
Okay.
So that's what we do. Yeah. But the kernel performance actually increases very quickly as you go down this tree. Usually with like 3 or 4 layers, you get very good models. And then after that, you're going to be stuck for a while. So there's 2 problems that you're going to be facing. One is that the number of kernel parameters is going to become so large that the problem will be highly non-convex, and just optimizing the marginal likelihood becomes a big problem. And second, of course, is overfitting. So we basically stop increasing the complexity of these kernels once we face those problems. Okay, but as I will show you, going just a couple of layers down this tree gives you a huge advantage. So if you allow me, I'll maybe show you a few examples before we break, because I think this is really interesting. So I've already shown you this curve. Yesterday we saw this curve, and so this was optimization with a randomly chosen kernel, which basically shows no pattern of convergence for this number of iterations. Like I told you yesterday, that Bayesian optimization is guaranteed to converge. What we don't know generally is how long it would take to converge. Like this shows no pattern of convergence on this scale of the number of iterations. But then, if you craft the kernels using the algorithm that I just showed you, you can see that the convergence becomes much faster. And as the kernel becomes better and more complex, and as you go deeper in that search tree, you're converging to this red curve that basically drives Bayesian optimization to the correct answer the most efficiently. So this is good. No, maybe not the most impressive example, but I wanted to remind you of that. Let me show you another example. So this is from the work of Jun Dai, one of my graduate students, who's been building potential energy surfaces with Gaussian processes. And again, our focus has been to build the most accurate global potential energy surfaces for polyatomic molecules with as few training points as possible. So this is a 6-dimensional system. And one of the things, so if you want to build a global surface with a very small number of training points, you need to be able to not only interpolate in this energy landscape, but also extrapolate. So, we wanted to see if our models are capable of extrapolation. And the way we tested this was by training the models within a small energy range of energies, and then looking at the performance of those models at higher energies. So here's one of the results for the model with 1000 ab initio geometries. So the model is trained by the ab initio points in the shaded range of the graph here of energies. And so everything in that wide area is the prediction of the model. So basically, the line here is the model prediction, and the symbols are the original ab initio points. So as you can see, like with just 1000 points, you can build very accurate 6-dimensional surfaces, and not only by interpolation but also by extrapolation. Now it gets better than that. So let's look at a 51-dimensional system. So this is for imidazole dimer, the work of another student, PhD student, Hiraki Tsukizawa. So 51 dimensions, 5,000 molecular geometries. I told you yesterday that as you scale things up, like as you increase the number of dimensions, you generally will need fewer training points per dimension. So we get similar accuracy for this system with 5,000 geometries. Again, so this is what we get for the extrapolation performance. We train this 51-dimensional model with the energy points in the shaded range, and we predict them in this open range of energies. The symbols are, I mean, the circles model, and the squares are the original ab initio points. All right, so it gets even better than that. So this is for the 57 dimensional surface for aspirin. So this is the work of Kasra Esnashari. He's a graduate student in the group as well. So he, so basically, to get this to work, we complicated things. So we basically built on the work by the other people who designed the so-called gradient domain machine learning method, which aims to build potential energy surfaces and force fields for polyatomic molecules by training models not only with energies but also with forces. So these models here, so this is the model of the potential energy surface and the forces experienced by each atom in the molecule, and these models are trained by potential energy and forces, or actually by only forces, at 400 ab initio geometries. So you have a 57-dimensional configuration space. Actually, the molecular descriptors that we use for this problem, they have to lift those 57 dimensions to 215 dimensions. So the model we actually build in 215 dimensions. But you see, you have a 215 dimensional problem, and that you describe with only 400 geometries in that 210 dimensional space. And as you can see, so what we're looking at here is the validation error. It's basically the error calculated on a set of something like 2,000 or maybe even 10,000 points that are not used for training the model. And this is as a function of the number of layers in that kernel selection tree that I told you about. So you can see that and so yeah, so these are the different kernels, like I guess the red dots correspond to the kernels with the lowest value of the BIC. So what basically this shows is that you can reduce the error of the model dramatically by this algorithm, and the BIC does remain a very good kernel selection metric, even when you have as few as 400 training points in this high dimensional space. And as you can see, there is a bit of a turnaround here, and this is what we mentioned earlier. It's due to overfitting. So we would stop, basically the kernel optimization at layer 3 here. Okay. Yeah. So and if you look at the actual accuracy of the model, so it's about 0.1 kcal per mole, which is like typically when people build the models of this kind of molecules, they aim at the accuracy of 1 kcal per mole, which is like the sort of ballpark of thermal fluctuations at room temperature. Now, what we're talking about here is a model, a global model of a potential energy surface for a 57-dimensional molecule obtained with only 400 ab initio calculations. So I think this is quite impressive. So go ahead. Is there a question?
Yes, there is.
Yeah. Please.
So you said that you're also using forces in order to compute the potential energy surface, and I wonder how many geometries are you using to compute the force at each point? So these 400, I think you
400
need
points. Yeah.
Yeah, but at least you need 3 times in order, like 3 times more in order to compute the force at a certain point, right? From electronic structure theory, you need like.
Yeah, sure. You need all
So in the end, like the computational costs are, I don't know, equivalent to maybe 1,200 points or even more.
Probably, yeah, probably, but it's still a lot less than what people normally would do. Yeah, we didn't do the ab initio calculation, so I'm not. I wouldn't comment on that, but for sure, yeah, it's more expensive to train with forces than with energies, because you have 3 components for each force, but it's still it's still a fairly small number. I should say that we don't use energies to train these models. So we use forces only. And you see, once you build a model, a Gaussian process model with forces, you can actually integrate it analytically because you have so you have kernels that are trained by forces, and you can integrate those kernels, and you can build a Gaussian process model with integrated kernels, and that's what we use to predict these energies. So yeah, so these models are trained by forces at 400 geometries.
Thank you.
Yeah, so these points, yeah, so it's not the number of training points, I should be clear, but the number of molecular geometries. When it comes to forces, it's really important to mention that. So
I actually have another question.
Yeah, go ahead.
These potential energy surfaces that you create, have they been accurate enough for use in like modern spectroscopic applications?
Maybe not. So not spectroscopically accurate, because, like I said, if you look at this accuracy here, it's 0.1 kcal per mole. So 1 kcal per mole is about what, 390 wave numbers. So this is about 40 wave numbers of accuracy. So it's so for spectroscopic applications, we want surfaces to be like close to 1 wave number, right? So yeah. But certainly for any kind of simulations of molecular dynamics, other than spectroscopy, like if you want to simulate like reactions, for example, especially at room temperature, this is definitely much more than necessary in terms of accuracy.
Okay, and could you quickly comment on what you think is the block to go to like something like spectroscopic accuracy, for instance?
Yeah, so this is actually a very interesting question. So it's actually not trivial to build surfaces with 1 wave number precision globally, and so with Gaussian processes, because what happens is that you get very quickly to this sort of precision of like something like 30 or so wave numbers. But going from there to 1 wave numbers, the tail is very, very long. So of course, you could of course reduce this error by increasing the number of training points. But this reduction is, it is proportional to 1 over the square root of the number of training points. And it's actually, in practice, it's actually even a little slower the closer you approach that extremely accurate limit of 1 wave number. So yeah, we've tried to do this on a number of occasions, and it's really difficult. Yeah, 30 wave numbers, maybe 10 wave numbers for global like 50, like 100 dimensional surfaces we can probably do. Getting below that is really hard. Yeah, so you need a lot of training data points that almost begins defeating the purpose then. And it's just I think the nature of Gaussian process models. I mean, like they will infer the main features and I guess fairly accurately, very quickly. But then if you want extreme accuracy from them, you really need to work very hard and yeah.
Sorry, following up this question, just as a follow-up,
yeah.
Is there any hope for Gaussian processes for spectroscopic systems? So I've seen like some PSs in literature, and they seem to be using like a lot of data points in order to arrive to this accuracy. And then, as you said, like this is contrary to the benefits of Gaussian processes. So would you try to also do Gaussian processes for these systems and for these requirements on accuracy?
Yeah, this is one of our goals actually, but you have to be creative to do that. So one of the, you have to be really then creative about how you design the kernels, I believe, and then. So I don't think this algorithm would be suitable for this sort of applications. What I think might work better is like if you were to build the actual potential energy surface evolution into the form of the kernels. Like for example, if you know that your potential is harmonic, you could you could use that as the kernel actually, and then yeah. So if you build that information into the kernels, I think that becomes a much easier problem. And yeah, so it's on our list of things to do. We haven't done this yet. And there's other, one of my former students has been looking at another approach using a spectral decomposition of, I think some sophisticated expansions of kernels in terms of delta functions, I think, and then he would get very accurate potential energy surfaces for something like aspirin, with the error approaching one wave number, not quite at the one wave number level, maybe like 5 wave numbers, better than us, but still not quite at the one wave number. And he would have to use more training points. So he would use like something like 15,000 training points for this, which, don't get me wrong, is still a small number. 15,000 points for a 57-dimensional system is still a lot less than what chemists would normally do to build surfaces for this kind of big molecules. Yeah, but for our standards, we want to, that's too many.
Thank you.
Shall we take a break now? Yeah, I suggest we take a break, maybe of 10 minutes, shall we?
Yes,
There's still a lot I wanted to tell you about. Yeah, so shall we meet at 10 after the hour?
yes,
Yes,
perfect.
in 10 minutes. Yes. So
Sounds good.
see you.
See you.
10 minutes. Okay, so I think we are back from break. Yes, and maybe in 5 seconds when people take seats, you can continue, Roman.
Thank you, Mika. All right. So we saw in our previous discussion that we can build Gaussian processes that can extrapolate, or at least we saw a hint of that in our analysis of the potential energy surfaces and the way we train them. So we wanted to actually see if one could, if one could build very complex models of complex physical quantities, if we could build predictions of this kind of quantities by extrapolation. So we applied the algorithm for the kernel construction that I described today to a few problems for extrapolation in the Hamiltonian parameter spaces for condensed matter physics systems. And so the problem that we considered in this case was one where, let's say you have a complex system and you know the observables, you know the solutions to the Schrödinger equation in some part of the Hamiltonian parameter space, and you want to make predictions of the same observables at some other part of the parameter space. And to make matters more interesting and more complex, we wanted in particular to see if one could design models of this kind that could extrapolate across phase transition lines. Let's say you have a system with multiple quantum phases, and let's say you know the properties of the system in one of the phases. The question that we were trying to address in this study was whether one can actually build Gaussian processes that could take this information on input and predict the locations of the phase transitions as well as the properties of the system in the other phases. Okay, so I'm going to illustrate that it is possible by two examples. So the first one is going to be the Heisenberg spin model. So for the Heisenberg spin model, you can calculate the free energy in the mean field approximation analytically. And this is what it looks like as a function of magnetization and temperature. Okay, so if you follow the minimum of this function, that's going to be the magnetization of your system. Okay, and it's plotted here as a function of temperature by the dashed curve here. So the dashed curve is the mean field result. Okay, so we wanted to see if one could build a model in one of the phases and then predict the location of this critical point here, the phase transition, as well as the magnetization in the other phase. And this is what we did. So we built the model by the free, we trained the model by the free energy of the system. So basically we trained the model in this shaded range of temperatures. And then we let the model predict the magnetization, or the free energy, and consequently the magnetization at temperatures below this line here. And so the symbols here are the model predictions. And again, the dashed line is the mean field result. And as you can see, the two are, agree quite well. So the model, the machine learning model can not only predict the paramagnetic to ferromagnetic transition temperature, but also the magnetization deep into the other phase, as you can see. Okay, here's another example. The other example is for the generalized Polaron model. So back in 2013, we studied Polaron systems where the electron, in which the electron is coupled to phonons by two types of couplings. One depicted here by H2. Well, actually, one by H1 is the one that basically modulates the potential energy of the electron, and the other coupling modulates the kinetic energy of the coupling. So one of them is the so-called Holstein coupling, and the other one is the so-called SSH, or the Schrieffer-Heger kind of coupling. So this is not important for our purposes today. So in any case, so if you look at the eigenstate of the Hamiltonian that describes polaron with these two types of couplings, and if you look at the properties of the polarons, they're going to exhibit two sharp transitions as a function of the as a function of the coupling strength and the ratio between the two types of couplings. So these sharp transitions, they basically separate the areas in the phase diagram that have polarons with very different properties, with very different ground state properties. And so we wanted, so this is what we discovered back in 2013, you know, for other reasons. So what we wanted to see in this study is whether you can actually build a model that would take the properties of the polarons in one of those phases and then predict the locations of these phase transitions, as well as the properties of the polarons in the other phases. So this is what we find. So again, the dashed lines are the results of the calculations that we did back in 2013. And the color-coded diagram is the prediction of the machine learning model that's trained by the properties of the polarons, the dispersions basically of the polarons at the positions of those white dots here in this graph here, and the positions of the black dots in the right panel. So this figure in particular is very interesting because you can see that the machine learning model can not only reproduce the nearest phase transition, but it can also predict the second phase transition that's separated from the location of the data points by the entire phase. Okay, and of course the predictions of the model are a bit more accurate when you train the model by the data from the middle phase here. Okay. Now, this series of graphs illustrates the importance and power of the BIC as the model selection metric. Because, you know, one question one might ask is, why not to just choose a very complex kernel, like a neural network is a kernel, and why not to, try and optimize that? Would that lead to any sensible results? And what happens in that case is shown by the lower row of plots. So this row of plots shows basically the results that one would get by training the models with kernels of the same complexity as the complexity of the kernels in the upper row, but chosen at random. Okay, so I go to the same layer of that kernel search tree, I choose a kernel at random, and then I train the best model with that kernel, and this is what I get. I get garbage. Okay. So, and of course, the top row shows what happens as you improve the complexity of the kernel using the BIC as the model selection metric. And again, this is remarkable because the number of training points here is very, very small. So we're training those models with something like, well, each one of those dots here represents a polaron dispersion, which is basically the energy of the polaron as a function of its momentum, which probably has like 100 points as a function of k. But then you've got something like 50 of those. So it's 50 times 100, so it's not less than 5,000 points in total that you're training those models. So this is a fairly small number of training points. Yet the BIC works perfectly well as the model selection metric. Okay, yeah, this is again the zoomed view, enhanced view of the same plots. One of the two plots from the previous slide. I just wanted to show it to say that what this illustrates is that choosing better kernels not only makes extrapolation possible, but also allows models to extrapolate farther. Okay, so in the language of what we're talking about, when it comes to searching quantum phase diagrams, I would say that choosing better kernels is like replacing spectacles with binoculars when it comes to quantum phase diagrams.
I have a question.
Yes.
Is there any physical reason why this extrapolation works? From
physical reason?
a physical reason for extrapolating from one phase to another without any knowledge of that phase?
Well, what happens is that, so our hypothesis going into this was that if you look at the evolution of the physical properties within one of the phases, as you approach the phase transition, the evolution of the physical properties should somehow reflect the fact that there is a phase transition. Like, for example, if you look at the polar dispersion down here, and as you move in this phase diagram towards the phase transition, the polar dispersion is going to change in some way that should reflect the presence of this phase transition. Now, you wouldn't see it by a naked eye necessarily, but that's what machine learning is good for. It's good for picking up correlations that you wouldn't necessarily see, but that would still be indicative of the change of physics. And that is exactly what I think happens. Those models, I think, pick up on this sort of correlations and how they change as you approach the phase transition lines.
Okay, thanks.
Yeah. Sounds good. Anything else? Shall I move on?
Yes,
Yeah,
please.
Yeah, because there's a lot more I wanted to say, and maybe I'll skip this. I just want to also mention that these kind of models can be used for many interesting, wonderful things. Like, for example, they could be applied for what we call transfer learning. So let's say you have a quantum dynamics calculation for some complex system, and of course, quantum dynamics calculations for complex systems are difficult, so we must always rely on approximations. And then the question that we raised in this study is, can the results of the approximate quantum calculations be corrected by machine learning? So in this particular work, we looked at collisions of molecules undergoing some collisional relaxation. We looked at cross sections for those, and we calculated the cross sections for molecular transitions with two different methods. One was the rigorous method without any approximations, and one that relied on the so-called coupled states approximation, but we're not going to go into those details. And so then what we did, we built Gaussian process models that now had not one but two outputs. And the two outputs were the exact calculations and the approximate calculations. And then those Gaussian process models would be trained by a large number of approximate calculations and isolated exact results for some certain quantum transitions. And then, the model would generalize the exact results to other quantum transitions for which we don't have exact calculations in the training set. And this is an example of what we get. So the dashed line here is the energy dependence of the cross section obtained with the approximate calculation. The solid line is obtained with the exact rigorous calculation. Now the solid line is not used for training the model. So the model is trained by this dashed curve and some rigorous results for some other transitions. And then the symbols are the predictions of the machine learning model. And you can see two things here. One is that the model actually works very well. And two is that, it also extrapolates beyond the energy range, where you have the training data quite well. I guess you could see that here in the shaded region. That's where we don't have any training data for the exact results. Okay, now I guess so. What I talked about today, what I tried to illustrate today, is three sort of applications of Gaussian processes with enhanced kernels that we build, like I showed you. The three applications I talked about were the extrapolation in the Hamiltonian parameter space, the improvement of the accuracy of quantum dynamics calculations, as well as the inverse problems. Okay, so I just wanted to show this picture here that was on the cover of PCCP, that to feature my paper there. The reason I like this picture, this diagram basically illustrates our ability to solve the inverse problems and our ability to extrapolate quantum problems with Gaussian processes. Now, what I like about this figure is this depiction of the inverse problems. You can actually, think of our approach as basically a cat walking on multiple potential energy surfaces simultaneously, and then looking at the observables and picking a potential energy surface from this manifold, from the distribution of potential surfaces. I guess in language of what actually happens, you consider molecular dynamics no longer as evolving on a single potential energy surface, but evolving on a distribution of potential energy surfaces, and which potential energy surface the atoms or molecules follow is determined by the experimental observables. You basically condition the problem by the experimental observables. That's the essence of our approach here. Okay, so yes, I've got about half an hour now, so maybe we could use this to discuss quantum machine learning. So so if you know how to build the right kernel, basically, so that's been the message that I've been trying to convey to you over and over again. So if you know how to build the right kernel, predictions are easy. So the question is, can quantum computers help maybe to build better kernels? Okay, so right, so better kernels lead to more powerful machine learning models, and we know that kernel functions are inner products in a Hilbert space, right? So let's now consider a quantum computer with n qubits, initially, say, in state 0, and introduce a sequence of gates that produces a quantum state of this kind. So those gates, they're gonna there's gonna encode somehow your input features. And let's consider another state of this kind, okay? Now, the measurable square of the inner product is going to be this, okay? So, and this thing has all the properties of a kernel of an RKHS, okay? So if you take this thing and you project it onto this state, this could be another way of building kernels for kernel machine learning, right? So it's basically, you would be building this, but now not by some mathematical functions, but by quantum measurements. So, and this of course raises these interesting questions. Can such measurements be used to build kernels for machine learning? What is the best way to build, if the answer to this question is yes, then the second question is, what is the best way to build quantum kernels for machine learning? And of course, the million-dollar question is whether quantum kernels can outperform classical kernels for machine learning. Okay, so we're going to discuss these questions in a bit. Before we do that, let's look at what is the RKHS with a kernel function produced on a quantum computer. So consider the embedding of input features into quantum states. And then again, we're going to define the kernel function as follows. Okay, then you can easily see that the kernel function is can be defined as the trace over rho of x and rho of x prime. Okay, so then the question is, what is the RKHS that corresponds to this kernel function? Okay, so in the RKHS is basically given by the set of functions that are given by basically these expectation values, where m is any Hermitian operator that acts on the space of these d qubits. Okay, so you can show that this k of x is actually, which is defined like so, is a reproducing kernel for each element of this space. Okay, now the next important question is, what is the dimensionality of this RKHS? It's actually fairly easy to answer this question if you look at it like this. So again, this is what we measure on a quantum computer, and we define it to be the scalar product of these two guys here. So each one of those vectors lives in the RKHS, and then these states, of course, are in the Hilbert space of the quantum computer with t qubits. So you can see immediately that this kernel function has at most 4 to the d non-zero eigenvalues. So the RKHS is going to be bounded from above. It's going to have at most 4 to the d dimensions. And then, of course, raises this interesting question of what implications does the finiteness of this RKHS have for problems that can be addressed with current day quantum computers? Because, you know, we can't really afford too many qubits, right? When we work with the IBM quantum computer, like maybe 6 or, you know, 4, but not many more than that. So that will limit the RKHS. What implications does this have for regularization problems? Interesting questions. So I'm just posing questions that we are actually kind of thinking about, you know, to kind of stimulate you to think about this as well. Okay. So again, what we said is that we can build this sort of kernels on a quantum computer, and this leads to these questions. And this is what quantum machine learning, you know, these days. So these are some of the questions that quantum machine learning these days is concerned with. Okay, so now the most important question, of course, is can quantum kernels outperform classical kernels? Okay, so this is a very important question to discuss, and the question, I guess the real question is, what does outperform mean? So a lot of people talk about quantum advantage, and that in the context of kernel machine learning would mean that we need to find problems and kernels that can be with kernels that can be simulated classically. That's number one. This implies that, you know, of course, kernels that can describe big data better than classical kernels, and it also implies that this is going to be relevant in the infinite dimensional limit for the input space. So yeah, it's a big data problems. Now, there's a lot of papers in the literature that attempt to come up with data sets that would illustrate a quantum advantage of kernels, like, for example, this one that was published earlier last year, in which they say that they construct a family of data sets and show that no classical learner can classify the data inverse polynomially better than random guessing, assuming the widely believed hardness of the discrete logarithm problem. So what they did basically in this paper, they started with the discrete logarithm problem that is known to be hard, and then they generated the data set, basically generated a distribution of two classes from the discrete logarithm problem. And this is sort of, saying that if we need a quantum computer to solve the discrete logarithm problem faster or you know, with a quantum advantage, then the classification problem that derives from it is also going to require a kernel that will have a quantum advantage. But these sort of examples are not really useful, because, you know, what we really want is to see if quantum machine learning is going to be useful for anything practical, for practical applications at the end of the day. And then there's this paper that came out very recently that actually, like after the 3 days of my meetings with you, I think you should be able to understand pretty much everything what they say in this paper. So let's read the abstract a bit together, maybe, because it's quite interesting. So it goes like this. It has been hypothesized that quantum computers may lend themselves well to applications of machine learning. In the present work, we analyze function classes defined via quantum kernels. Quantum computers offer the possibility to efficiently compute inner products of exponentially large density operators that are classically hard to compute. However, having an exponentially large feature space renders the problem of generalization hard. Furthermore, being able to evaluate inner products in high-dimensional spaces efficiently by itself does not guarantee a quantum advantage. And this is a very important statement, because a lot of times people will say that, well, you know, we can evaluate very, you know, kernels on a quantum computer that are very difficult to simulate classically, but that is not sufficient to basically say that these kernels are going to have a quantum advantage. These people say that already classically tractable kernels can correspond to high or infinite dimensional reproducing kernel Hilbert spaces. Like the RBF kernel has an infinite dimensional RKHS. Okay, so just because you're dealing with very complex and high dimensional spaces and very complex kernels doesn't mean that such kernels are going to be useful or are going to have quantum advantage. That's basically what this paragraph is saying. So we analyze the spectral properties of quantum kernels and find that we can expect an advantage if their RKHS is low dimensional and contains functions that are hard to compute classically. So you see what they did here, they actually looked at the scaling of the kernel eigenvalues. Remember I talked to you about the kernel eigenvalues on our first day of meetings. So they looked at they analyzed the eigenvalues of these quantum kernels, and they showed that as you make the quantum computer bigger, these eigenvalues are going to become all very small. And remember what I told you on the first day of our meetings, like if the kernel eigenvalues are 0, that basically makes a part of the function that's not in the RKHS not learnable. So small eigenvalues of the kernel of an RKHS makes basically, if all of the eigenvalues are very small, it makes these kind of kernels basically useless for learning, I guess, for solving regularization problems. So, and that's what they find. They find that if you take a quantum kernel, like the one I introduced, and then you include, you consider a very big quantum computer, scale it up, all of the eigenvalues of the kernel are going to become very small, which basically says that those kernels are not going to be useful. So, but they also consider that, well, basically say, but if you limit the size of the quantum computer, you can build useful quantum kernels. They say that this implies that if the target function is known to lie in this class of low-dimensional RKHS, and it is hard to compute classically, then quantum computers can potentially have a quantum advantage, as the quantum computer can encode their inductive bias, whereas there is no classical efficient way to constrain this function class in the same way. However, we show that finding suitable quantum kernels is not easy because the kernel evaluation might require exponentially many measurements. So in conclusion, our message is a somewhat sobering one. We conjecture that quantum machine learning models can offer speedups only if we manage to encode knowledge about the problem at hand into quantum circuits, while encoding the same bias into a classical model would be hard. And these situations may plausibly occur when learning on data generated by a quantum process. However, they appear to be harder to come by for classical data sets. So I strongly recommend that you read this paper if you're interested in quantum machine learning, because you'll learn a lot about how quantum machine learning works and some of those interesting conclusions that they and conjectures that they come up with. Like I said, it's quite interesting to think about. So I guess the bottom line of this is that the jury is still out on whether quantum machine learning may have a quantum advantage. So perhaps there is no practical quantum advantage to present day quantum machine learning. Okay, so then maybe we could talk about the outperformance of quantum kernels in the sense of better inference. Okay, because as we saw throughout my presentations, building good kernels is extremely important, but it's actually not trivial. I mean, like, we use this method based on the BIC, but it's a greedy search that is, still leaves many good kernels out of the search space. Okay. Now the question is, can perhaps quantum kernels offer an alternative to classical kernels? And so what if you think about this is simply another way to do classical machine learning, but now by building kernels using quantum algorithms, so that there would be no quantum advantage per se to this kind of kernels, but that could be just another way to approach the kernel construction problem. Okay, so so that's one of the questions that we consider in many of our studies in my group, and basically, what does better inference mean in this context? Basically, you want to aim to make more accurate predictions with the same and usually small number of training points. You want to make more accurate predictions with quantum kernels than with classical kernels. Okay, And of course, if you want to show that it is possible, you need to be able to find the best quantum kernels out of all possible quantum kernels. Okay, so these are some of the central questions that we work on. So I guess, can quantum kernels be used to build useful kernels, and what is the best way to build quantum kernels for machine learning, right? So yeah, so let's maybe take 5 minutes or so to discuss how quantum machine learning models are built in practice. Okay, I mentioned before that we're going to embed X into the quantum circuits. So how is this actually done? Well, you're working with quantum circuits that are depicted by something like this, where you typically, like with the IBM quantum computer, I guess these days, you have access to something like 4 to 10 qubits or so. Okay, so the simplest possible embedding could be just to set the phase of that Z rotation to the value of one of your input features, and then you would need. So for this sort of embedding, you will need as many qubits as the number of input dimensions, 1 qubit per dimension. Okay, so you can embed your features into the circuit in this way, and then you can entangle your circuits using, for example, CNOTs. Okay, and then another strategy could be to embed using a combination of 1 and 2 qubit gates, for example, by setting those phases here as proportional to the, this is what other people have done, proportional to the input features, and then these phases given by something like this. Okay. All right. So yeah, we're going to use both of these types of embedding in the examples I'm going to show today. So we're going to take a quick look at 2 types of problems that we're solving with quantum kernels, the interpolation and the classification problems. We're going to start with the problem of building the same potential energy surface, 6-dimensional potential energy surface for H3O plus, but now on a quantum computer. Okay, so now with a kernel on a that's built in a quantum computer. Is there a question out there? Okay, so so this is actually the surface that we do obtain as a result of our calculations. The surface built with the quantum kernel, so it looks nice and smooth, but it took us a while to get there. So this is what we would like to see, this sort of a plot. We've already talked about it. So when June Dai, one of my students, did it, his first attempt looked like this, and his second attempt was this, and his third attempt was that. Okay, so and this is what produces a fairly accurate surface. And let me show also. Well, so to do this, actually, June had to invent many things. Like, for example, he had to design a way to optimize the parameters of the circuit, because he was basically building Gaussian processes with quantum kernels now. And so how do you optimize the parameters of quantum circuits? You don't have these analytical expressions anymore, right? So yeah, so this is where Bayesian optimization is extremely useful for. So June actually applied Bayesian optimization to optimize the parameters of the circuits to obtain these sort of results. Okay, so what these sort of exercises allow you to do is look at things like, for example, the role of entanglement for the performance of the kernels. And what I have here is the validation error as a function of the energy cutoff. So what I have on the x-axis is the energy of that, the top margin of that shaded region. And then we use these models to extrapolate and calculate the error in the extrapolated region. So if you don't include any 2-qubit gates and build a kernel for your Gaussian process model, then you get this sort of the error. So the blue circles. Okay. Now, if you entangle the qubits by C0 case, as June did, then you will get the green triangles. And as you can see, these sort of kernels, they outperform the RBF kernel, even at, especially at, for the problems where you have to extrapolate further, so basically for the problems that are trained with a narrower range of energies, with data in a narrower range of energies. Okay, so yeah, so these are all preliminary results I'm showing you. I mean, we haven't published this yet, but I wanted to share this with you nevertheless. So another student of mine, Elham, she's looking at how best to build quantum kernels, and she's working on classification problems. And the examples I'm going to show you, they are for this particular classification problem. So for perovskites, which are compounds that have this crystal structure, and so depending on basically the electronegativity, for example, of the different atoms and other parameters, depending on the electron affinity, the ionization potential of these atoms. So the perovskites are going to be metals or non-metals. And that's what Elham is classifying. She's trying to build a model that would take, for example, the electronegativities of these atoms and predict if the corresponding perovskite is going to be a metal. Okay. And the purpose of what I'm talking about now is to show that the classification results. So she basically uses quantum SVM. Remember, we talked about SVMs, and we said that the way SVMs work, you fix the kernel, and then you optimize those alpha parameters. So what Elham does, she builds the kernel on a quantum computer, with simulated qubits at the moment, and then she optimizes the alpha parameters to basically build the quantum, the SVM model, but the quantum kernel. And I guess maybe this is what we should look at. So what this shows is the accuracy of classification, which is of course the greatest at when it's equal to 1. For the two classes, there's the class of metals and the class of non-metals, and this is as a function of the number of layers in the circuits that are used to build quantum kernels. And as you can see, the error fluctuates all over. So, which basically is to say that the way you design those quantum circuits for quantum SVM matters quite a lot, and then of course raises the question of how should one build proper quantum kernels. So this is one of the algorithms that Elham came up with. It's a greedy search algorithm that builds those quantum circuits layer by layer. So she would start with a quantum circuit that has, say, 2 layers of gates. It's a 4-dimensional problem that she's considering, so hence 4 qubits. And then she would train, go through all of the combinations of gates, train all these models, and then select 20 models with the highest accuracy. And then she would add the 3rd layer and to those 20 models. And so you see this algorithm it resembles the kernel selection algorithm that I told you about, but it just basically builds layers of these quantum circuits that yield quantum kernels layer by layer. So she would take those 20 base models and then combine them with all possible combinations of gates in the 3rd layer, and that will produce 1,400 combinations. She would select 20 best of them and iterate this procedure, and this is what she would get. So again, it's a process that involves building circuits by layers, and as you can see that as you increase the number of layers, the accuracy of the quantum SVM goes significantly up. And so the yellow curve is the one with 5 layers, as opposed to something that down here, which is 3 layers. Okay, so I think I'm going to maybe maybe I should also say this. So one of the problems with quantum kernels is that you actually need to build the entire kernel matrix on a quantum computer. And for problems like kernel ridge regression or Gaussian processes, it's actually it's very is difficult because you not only have to build that kernel matrix, you have to build it many times as you optimize the hyperparameters. And this is very expensive to do on a quantum computer. So one of the problems that June is working on is,
Yeah, can you come back on the results like the previous slides?
Yeah,
so this does not depend on the number of qubits, as you mentioned.
No, so yeah, the number of qubits is fixed because the number of qubits has to be equal to the number of features. And so it's a 4-dimensional problem that Elham is solving. So the number of qubits is 4.
Yeah, okay, thanks.
Yes, it's just the gates that we're changing. Okay, so
I have another question.
Yeah.
Did she only use single qubit gates or also entangling gates as well?
yes, on the C0s. So it's only U1s and C0s that she uses, I think, in this approach. Yeah. But because we don't know a priori how to distribute those gates, how to combine those gates, I mean, that's why we need some sort of an automated machine learning approach to do this. So our next step in this process is actually to use BIC to drive this circuit selection process, which we haven't done yet, but that's what Elham is doing at the moment. So we'll see how that comes out of it.
I also have a comment.
Yes.
Some paper, there is a recent paper of Maria Schul that is actually showing that this kind of variational quantum circuit at the end are doing some kind of Fourier transform.
Yeah.
So the thing is that a trick that you can use to have more expressivity is to re-upload your data. No? So here what I see in your circuit is that you're actually only doing one time the embedding of your parameters that you want to optimize.
Yeah, that's right. And so the result of Maria Schul applies to, I guess, in order, so you're talking about the paper where she showed that you can build a universal approximant to a function, you know, by properly selecting the embedding, I guess. And that, but that would require potentially a very large number of gates. So it's a hypothetical example that we don't have a luxury. We can't afford it at the moment because, you know, like we can't really build circuits with a very large number of layers here. So we're limited by the number of gates we can work with, and that, of course, that's why we need an approach like this one to really tell us what's the best combination of all those gates within a fixed number of layers and a fixed number of qubits.
No, this I agree, but I think it's important to also take into account that you can like have gates that are actually parameterized by the parameters that you want to optimize, because this gives more.
Yeah, for this we use Bayesian optimization, but there's a few other tricks that June had to invent because it doesn't work as in a straightforward way. Because, you know, the optimization has, I mean, the marginal likelihood in that case diverges for some reason, and it's very difficult to optimize. So you have to fix those, you know, divergences. But yeah, I don't have time to go into that discussion. Also, it's not yet published. But yeah, I guess I wanted to conclude by also mentioning that the other thing that limits the application, I mean, basically the application of quantum kernels is the fact that it's very expensive to evaluate them, right? So you have to basically perform quantum measurements for every pair of your training points to build your entire kernel matrix. And yeah, and if you have a lot of training points, you know, these are big matrices that we're talking about, so it's very difficult to do. And so what June is doing, he's actually trying to build a bigger kernel matrix out of smaller ones. So he's developing machine learning techniques that would interpolate or extrapolate the the kernel matrix elements that are evaluated on a quantum computer. And you would see something like this. If you look at the relative error, well, I guess this is for a problem of with 1,000 with 10,000 10,000 kernel elements, and so he can actually estimate those kernel elements with as many as with as few as 100 to 1,000 I guess quantum measurements. Kernel matrix elements. Each kernel matrix element is going to require something like 1,000 quantum measurements. But instead of evaluating 10 to the 4 of them, you can actually design strategies that would interpolate a much smaller number of them to get you the full kernel matrix. And like I said, June can do that with something between 100 and 1,000 kernel matrix element evaluations to build the full kernel matrix that gives accurate models. Okay, so I'm running out of energy and time, so I think we should stop here. I just wanted to maybe finish with this diagram that sort of represents our approach, our thoughts about quantum machine learning. So the big questions that we're thinking about are, of course, how to build the best quantum kernels, and can quantum kernels outperform classical kernels? But an equally interesting question to ask is whether these sort of algorithms, like the one I mentioned that Elham is working on, those algorithms, they're not going to have a quantum advantage. I mean, those kernels are going to have quantum advantage, but they may ultimately lead to kernels or quantum kernels that will be better than anything that you can construct in a straightforward way with classical algorithms. And that could be exploited for better classical machine learning. And this is what I'm hoping that we can show in some not too distant future. So I'm gonna stop here. Thank you for your attention. And yeah, so if you have any questions, like I said, feel free to reach out. I'm gonna stay here for as long as you need me.
So thank you very much for this exciting series of lectures. So we can thank Roman maybe. And
so are there any immediate questions, or are you guys, do you guys have to go? Because it's I don't know what time it is, 11 o'clock, right?
so the question, yeah, maybe do we have some still urgent questions in the room? Please remember that it's 2 a.m. in Vancouver, and we are very grateful for Roman for spending his midnight with us. Yes, so it seems that there is no really questions. So yes, so thank you once more.
Yeah. Well, you know how to reach me, so yeah, feel free to reach out, like I said, and all the best, and have a great rest of the school.
Thanks a lot.
All right.
So now we have half an hour break. Goodbye.
Bye now.
Now half an hour break, coffee break.
2 short announcements. The speakers that are speaking in a moment. So Rafael and Lorenzo didn't send the PDF slides in PDF. Yeah, I didn't ask you before. No problem. So please do that. And I wrote to people who are regarding organized reimbursement of travel costs for. So just if someone wanted reimbursement and doesn't have an email, please also contact me. And yeah, so take a look at the email. Yeah, this time not Discord. So yeah, and enjoy the coffee break.